thanks to the organizer for this opportunity to talk about these two topics today. My name is Bussieres. I work at IDQ and at the University of Geneva. And I have quite a generic title, but I'm going to jump in a bit more details right away. There's going to be two parts in this talk. The first part is really about how to speed up QKD. And I want to focus here mostly on the detector part that was used in some recent experiments. That's going to be the first part. And the second part is going to be about IDQ's QRNG chip and with a focus on its security model. Okay, so let's just jump in already in the first part here. There's been, for many, many years now, there's been a lot of QKD work being done at the University of Geneva in the group of Hugo Binden. Now, since 2014, there's an activity in the SnSPD part, and naturally the goal is to develop some detectors for the requirements of the experiments happening there. So this is, I want to talk about this essentially, how we've been using these detectors to satisfy the needs of the QKD experiments and also other experiments, but I'll be focusing on the QKD part right here. Okay, so this, for a couple of years now, there's been a workhorse system that's been used at the University of Geneva for doing QKD, and this system is using the BB84 protocol, 3 states and 1 decoy. My focus here is not on this, but I'll briefly go over it so that you have an idea of how it works at a high level. So the idea here with this system is to be resource efficient. Okay, what I'm going to activate the laser pointer. Hopefully you can see that. Louis, can you see the laser pointer? Oh, okay, excellent. So the idea is to have a resource efficient approach. So by reducing the number of states in the protocol, and then also by using only 2 intensity levels, 1 decoy, you can also minimize the requirements on the hardware. And hopefully, if this ends up being deployed in a large number of systems, then you can have some minimization that can be quite useful there. So the idea of the protocol is to use these 3 states here, 0, 1, and plus. It's a BB40-like protocol. It's encoded into time bins with the 1 time bin here and nothing there is 0. This is the 1, and here you have the superposition of the 2, which gives the X state. The security of this protocol was proven in this paper here. And actually, the 1 decoy approach is interesting because it actually provides, in some regime, the ability to increase the key rate with a non-negligible percentage level, and that was shown in that paper here. So in practice, you have an Alias, you have a Bob. So Alias has a pulse laser, an interferometer to create the time bins, intensity modulation also for the time bins and also the decoy states, some compensation for fiber dispersion, a variable attenuator, and on Bob's side, there is an interferometer for measuring an X basis and a detector to measure in the Z basis. Back in 2018, the goal with this system was to go towards very long distances in optical fiber. So in order to achieve this goal, we developed some SnSPDs that have the potential of having very high efficiency and very low dark count rate. And actually, we achieved a dark count rate of 1/10 of a hertz with about 60% system detection efficiency, which led to QKD over 400 kilometers. So that's not very recent news. This was presented 2 years ago in QCrypt. It's an interesting result that was attained thanks to the development on the detectors. And since then, other groups have demonstrated QKD over even longer distances using the twin field approach, for instance. Okay, so the next target for this system was to go to high rates at shorter distances. So a bit more details about this system. The repetition rate is 2.5 gigahertz. The pulse durations are 30 picosecond, and then intensity is modulated at 5 gigahertz. And in order to achieve high rates, you really need to work a lot on the post-processing part. So the sifting actually is able to deal with up to 200 million detections per second, quite a lot. The error correction can operate at up to 100 megabits per second, and the primacy amplification is geared up so that it can, in principle, generate up to 60 megabits of secret key rate per second. Okay, so quite a beefed up system. Now, in order to achieve this potential, you really need to work on the detection part to achieve this, okay? And that's what we wanted to do here. And then in order to achieve this, we had to work on a new breed of detectors. We really wanted to have something that could go high up there, but still keeping this resource efficient approach, because one way you can do it, you need to beat the recovery time of the detectors. So one way you can do it, or you can try to do it, is by essentially putting a lot of detectors in parallel, either with beam splitters or multi-pixels and so on. But at some point, if you want to have 32 detectors or even more, you're going to have some other constraints to deal with, which is the time processing, the time tagging, and the time processing that you need to input there. You're going to have to also increase the cooling power of your cryostat. We wanted to keep things relatively simple, a relatively low power cryostat with a small number of detectors in order to have something realistic that can hopefully be deployed in different locations without having too much cost into it. So we worked on the detector part in order to achieve something that would approach these requirements here. So in a nutshell, I'm not going to spend a lot of time on this, but SnSPDs is an activity that started, as I was mentioning, in 2014 at the University of Geneva. We are working with molybdenum silicide SnSPDs. We're making them directly at the EPFL in Lausanne. And the operation principle is the following. You have it's not a nanowire, it's more like a nanostrip, something very thin and relatively wide. We're still talking about nanometer scale devices. You have this superconducting material, you cool it down to below the critical temperature, and you bias it below the critical current. And when a photon comes in, it's going to break a large number of Cooper pairs. So you weaken the superconductivity here, and then the bias current interacts with that and creates a resistive region. When you bias the circuit, the detector in a circuit like this, and the detector is modeled like a kinetic inductor in series with the resistance either 0 or something of the order of 1 kilo ohm, the current goes in here, and when it switches, it's going to leave that branch, go into the amplifier. It's going to create this very sharp rising edge right there. And then when it becomes superconducting again, because there's no more current in it, it will more slowly be rebiased by the current that's coming back, and the dynamic is governed by the ratio of this inductance over either this, something large, so quick unbiasing when you have a detection, and then it's slowly coming back because the dynamic is governed by this resistance here. So this LC circuit is rebiasing more slowly. So you get a pulse like this. Now, if you want to detect fast, you need to have something fast enough, but there's a limitation. You need to cover the optical fiber surface with this, so you have a certain length that will affect this kinetic inductance right there. And then if you try to operate at very large detection rates, you may be faced with latching. Latching is a situation where the detector gets stuck in a permanent or semi-permanent resistive state, and the only way to get out of that is to take the current back to 0 and then back up to the value you want to operate. And if you want to do a QKD system and you end up in this latch state, that's not going to be allowing you to go to faster speed. So how do you get beyond that limitation? Well, we wanted to try the following, and the idea was inspired from photon number resolving SnSPDs, which were demonstrated as early as 2008. The idea is intuitive. Instead of having this, you take your area and you divide it into several sections and you connect them in parallel. So something like this here. So each of these is one of those pixels that you see there. There's 3 here and 4 there, but you see what I mean. And intuitively, you'd say that if you have one detection here, this becomes disabled, but the other ones are still there to actually detect. So you have a couple of detectors in parallel available for detection, and you can perhaps hope to have a greater detection rate there. The other benefit of doing that is that each length is shorter in distance, in length, so you're going to have a smaller kinetic inductance, and you can hope to have everything working at a faster speed. There's a limitation, however, which is crosstalk between these different pixels. So when this becomes disabled, the current leaves that branch, and the other two are going to pick up the leftover along with the readout. And therefore, if you operate very close to the critical current of each of these sections, then you may actually force these guys to click as well. And if everything clicks simultaneously, the whole thing is going to reach a latch state. So that can be a real problem. So this electronic and also thermal crosstalk, you need to take pay attention to that. So we wanted to try this and actually we knew this wasn't going to work, at least with our preliminary test. And moreover, this idea of counting fast with these parallel detectors was not found in the literature so far. So we tried the following strategy. We had to be a bit clever to allow the system to mitigate this crosstalk. And the idea to actually achieve this is by adding on chip something else that's going to absorb the extra current, so that it's going to minimize the crosstalk between these two. And actually here I'm showing one extra wire, but in practice it's a lot more. It's, if you have let's say 8 pixels here, you can have as high as 40 or the equivalent of 40 nanowires outside of that. So it's as if you have a lot of nanowires to absorb the crosstalk, so then you're not going to be impacting the other exposed wires. Now, these are exposed to light, and these are not exposed to light, and that's the trick. Another trick as well is to make them wider so that if everything clicks, not everything is going to be, well, everything is going to go there and in the readout circuit, but not everything is going to be resistive, so the whole device will not necessarily latch. So you can opt to be able to go to high detection rates. Now there's a trade-off, of course. You don't want everything to go in there and not in the readout, because you need to have some part in there and some part in the readout so that you can have a signal at the outside that you can still discriminate. So it's a matter of really playing with the design. There's lots of parameters to tweak, and we managed to make this work. If you look at an SEM image of the detector, it looks like this. You have this section there, which is divided into 8 sections that are exposed to the light. Everything around is not exposed to the light, so they cannot click because of light. And then here you have a couple of detectors. Each parallel nanowire here outside, these unexposed ones have their kinetic inductance and then their series resistor. So how well does it work? So if we compare to a single, let's say classic SnSPD, here we're taking one that is rather slow, but still it increases the dramatic effect of having something that's better, but still it's not too far from the best ones that you can actually get. You're going to have a system detection efficiency that's going to be decreasing as the detection rate increases, because you hit this recovery time there. And if you see something here that starts around 80%, it's going to go down at some point. And here for this nanowire at 10 megahertz detection rate, you have a pretty big hit on the efficiency there. So how do you get rid of that? Well, we try this approach with these parallel nanowires, and actually you can start still with a very good efficiency, close to 80% at 1550 nanometers. And then you can look at how far does it go. Actually, for this one, we can still detect at 100 megahertz with CW light at the input. So random times for photons arriving, which is the configuration that looks the most like a QKD system. And we have this very good, we don't take a hit. Actually, this detector is not able to count at 100 megahertz at all, but this one can. And then there's no latching effect. You can crank up the power and don't have latching. So that's good. It's a good sign that we can use this in a QKD system. In a QKD system, you need to operate it mostly in that regime. You don't want to take too much of a big hit on the efficiency. And the jitter is between 60 to 100 picosecond. I'll be talking about that a bit later. And the dark count rate is about 100 hertz or less. You can play tricks and try to lower that as low as 10 hertz or even less. Now, to demonstrate that this actually works, we also made parallel SnSPDs without the necessary protection mechanism that the other nanowires around. And if you operate these close to the critical current, then you're going to count. And at some point, they have a high probability of latching here at 20 megahertz. So to get rid of that, you can lower the bias current so that when you do have this electronic crosstalk, it's not going to be impacting too much the other ones. But by doing that, you lower the efficiency. You can count faster, up to 100 megahertz here, but you have an impact on the efficiency. So that really shows that there's an advantage with this approach that we have. So there's latching and you have a lower efficiency. So putting all of this into the QKD experiment looks like this with 50 kilometers of ultra low loss fiber and an attenuation of 8.7 dB. We've been able to achieve a raw Q rate of 27.8 megabits per second and a secret Q rate of 8.7 megabits per second, which is a very good result for this distance here and that amount of loss. We can lower the loss and achieve a higher rate, but we're not, as you can see, we're not achieving the electronics or the full potential of the system there. So there's still some work to do on SnSPD. This was with 4 detectors here. There's still some work because there's still not a drawback, but there's still a limitation with this approach, which is the jitter. If you have too much of a jitter, you're going to have detection spilling over in the next bin, and that's going to increase the QBER, and you're not going to be able to do QKD anymore. So this jitter actually does increase with the detection rate, which is a limitation of any SnSPDs, because the jitter of an SnSPD decreases when you decrease the bias current. So when you start hitting the recovery time of your detector, you're going to take a hit on the jitter. So that's the limitation that we have to deal with right now. And there's, the way forward to realize these 50 to 60 megabits per second with such detectors is really into optimizing the design, optimizing the material, and hopefully get to 25 to 50 megacounts per second with at least 50% efficiency, but I think we can do better here, and deal with this jitter stability problem. And then, of course, you can increase the number of SnSPDs, but if you put 8 detectors, each having 6 or 8 pixels in parallel, then you're going to end up with a machine that doesn't have too many coaxes and inputs to time tag, but still have a lot of power for operating at high rates. Okay, so that comes to the end of this first part. I want to say big thanks to everyone at the University of Geneva, the QKD and the SnSPD team. And the results, the detector result that I just mentioned are submitted. They're going to be appearing on the archive soon. Okay, so that brings me to the second part of my talk, IDQ's QRNG chip and its security. So IDQ, you may have heard about this. IDQ has now a chip that does quantum random number generation. And the goal is to disseminate it into many devices. And IDQ wants to offer a path to quantum security to the people buying its devices. Now, ideally, we'd like to have QKD everywhere, but as you know, QKD is still rather expensive technology. It's still bulky, so it's not something you can put everywhere. It's not for everything at the moment, but there's still a path that you can take that can, in the future, lead to have the maximum security that quantum technologies can actually offer. And this path is first by using a good way to generate your random numbers. So the QRNG, we believe, is a good way, and that's what I want to talk to you about today. And then Alias can generate a good random key and then distribute that to Bob using a post-quantum algorithm, which is believed at the moment, at least not shown to be insecure against a quantum computer. And then for some situations where you need long-lasting security and then the budget is there to actually accommodate it, you can go to quantum key distribution. The nice thing as well is that this chip here is small, so low power consumption, so you can actually put it in a QKD system that also will reduce in size as time progresses. So why do QRNGs help? Because they're not the only kind of RNGs out there. So QRNGs help because we believe they do, because they offer a clear and robust entropy generation mechanism with the security tool. And that's really, I think, the extra you can get with such devices. What do we need to make them ubiquitous? Well, you need low production costs for mass market. So CMOS IC compatibility is a plus, which is the case with these devices. Small footprint, low power consumption, and you need to have some compliance with security standards such as FIPS, NIST, or common criteria AI-SWR. So the idea behind the chip dates back from a paper in 2014, QRNG on a mobile phone. And this paper made the realization that essentially all the cell phones in 2014 and still today have a camera that is able to see the fluctuations of light. Okay, so a CMOS image sensor is at the basis of everyone's cell phone camera. And each pixel is essentially a very, very good photodiode with high quantum efficiency and low noise. And then you have an amplifier. So you take photons and you convert that into electrons that carry the entropy of the photons here, or the photon number statistics, and then you generate a voltage, put that into an ADC, and you have a bunch of bits here that will be impacted by the randomness of the input right there. So each pixel in a camera is rather slow, but you can put millions of them, as you know, and therefore you can parallelize the whole thing, and you can hope to get some good rates out of that. Okay, and so the industry compatible elements are there. So in this paper from 2014, an LED, which is a multimode thermal source, which is yielding a Poisson photon number distribution, was shown onto a camera. And if we look at one of these, for instance, from the Nokia N9 phone that was used back then, this produces after the ADC a code. It's a 10-bit ADC, so it produces a number between 0 and 1023, and it produces a distribution. And the distribution you see there, if you just put it back towards 0 for looking at the width, and you compare that to the noise that's coming out when you have no photons at the input, you see that the distribution is much wider. And actually, this distribution is directly given by the photon number statistics that you have you are producing from the LED right there. So that's already a very good indication that you do capture the randomness that you have there. So you produce this 10-bit ADC. Now it turns out that with the code size and the intensity, you want to work in the right regime, and you're going to produce a code. So it's kind of like you draw one of these numbers at random. And then in this 10-bit ADC, well, the most significant bits are not going to fluctuate a lot. Actually, they don't carry entropy. They're very predictable. The least significant bit varies a lot, of course, but then it can be influenced by the classical noise that you want there. So actually, it turns out that these are the ones that vary the most. And you can prove that here you have about 5.7 bits of entropy. Now, if you want to get a high entropy output out of these 10 bits, you need to run it into a randomness extraction, which was done outside of the phone. So it's not yet a format that allows to directly put it into a chip. There's still some work to do outside. And one trick to make this happen is actually to realize that you don't need all these bits. You can just keep bits number 2 and number 3. Okay, so you don't need to use all of it. And that's what the IDQ chip does. Okay, so the design and so on has been going on for many years. It's now available commercially. And the idea of the chip is the following. You have this CMOS image sensor dedicated for the generation of random numbers. It's, again, a Poisson statistic source. It goes to the ADC. You keep bits 2 and 3. And you have your quantum entropy directly at the input. And the input distribution is this one here. There's also a DRBG for dealing with potential remaining bias there, but I'll be talking about this a bit more later. But I just want to focus on the quantum entropy right there. So these 2 bits here, if you want to convince that it's going to give you a high entropy output without having to do any extraction, well, you can look at this distribution here. So from edge to edge, it's about 100 ADC codes, okay? And keeping these 2 bits only, it's as if you're going to produce 2 bits, and you're going to flip which one of these bits that you actually keep every 4 codes. So 50 to 53 is going to output 00, 53 to 57 is going to output 01, and so on. So all the green ones output 0, all the red ones output 01, 10, and 11, and so on. If you take this whole thing and you kind of put it there, and you could try to see if everything is exposed uniformly, then you actually realize that it is. But you can make this more formal, of course. I'm going to show it. But essentially, that gives you already an indication that you should be able to provide high entropy output out of that. So let's go into the physics of each pixel a bit more. You have this photon number distribution. Here you have some loss. Loss is just a beam splitter. It only decreases the mean number, but you directly transfer these statistics into the number of photon generated, and you can have some dark electron noise. So also having a Poisson distribution, you're going to add these 2 together, and you get a total electron number that goes into a conversion. So you want to convert each electron into a voltage. So you do that here, and by doing that, you also add some Gaussian electronic noise. So you have a voltage here, analog value, quantum plus this noise there, and you feed that into an ADC, which gives you a sequence of 10 bits. So there's an effect here that is subtle, but it's important to mention. You have some pileup of the ADC code. So if you look at the whole process, this machine basically transforms one electron or a couple of electrons into ADC codes, and it's not one-to-one. And actually, in most of the cases, one electron is going to be just a little bit less than one ADC code. Okay? And that's why, so if you have that, so this conversion factor here is a fraction of one ADC code step provided by one electrode. Okay? And of course, the ADC is going to be doing some quantization. So if you have one electron, you may hop over the ADC code. The second electron you also hop over, but the third one, it may not be hopping over. So you're not going to be increasing the ADC code. So that gives rise to this pileup there. Okay, so that's a classical simulation. Or sorry, that's a simulation of the device that we should be seeing with the actual measurement. So is that a problem for entropy? No, because of the way, because of the fact that keeping bits 2 and 3 allow us to still have a fairly uniform distribution of the different 2 bits output. And if you just measure it, you get something like 1.94964, which is very close to the maximum you can get there. Now, you also need robustness to light intensity and non-uniformity in the exposition. Of course, like not every pixel is exposed or illuminated the same way. So if you, again, run a simulation and you make sure that the intensity is in the right range, that is not underexposed or overexposed, in this right range, you have a flat section where the entropy is near optimal. Right? So let's go have a look how it actually works in practice. So here we see 4 pixels on the CMOS image sensor. You can see that they don't have the same mean value. This is more like 550 and 450 here. So we do see the pileup effect, which is expected from what I just explained here. And it does look consistent with the Poisson distribution. As you know, a Poisson distribution, the mean is equal to the variance, so it should get wider as you increase the mean there. So to verify this, you need to take into account the conversion given by the ADC, so that translates it into a variance that varies like something that's proportional to the mean value plus an offset of ADC, and that's what we see there as expected. So we're comforted in the fact that it looks like it's working like as it should. Now, what about the noise? If you switch off the light here, you're going to be left with a small distribution that's like very close to 0. This one here, mean value around 10 or so, and you have some structure into it. And actually, you kind of see the periodic structure of the pileup effect. That's normal. That comes from these dark electrons there. So you don't have these, you have only that. But these also contribute to this pileup effect. And that's smeared out with a Gaussian here. So you have this shape here. So you can try to fit that, fits very well. And you get the values for these here. And you can know how much noise E can exploit. So this side information is something that you want to know how much it contributes to. So intuitively, you can just like look at this and imagine how much this can allow Eve to guess which of the codes here you're going to get. And actually, it's not a lot, but you can make it formal and calculate this guessing probability. So the way to go is written in this paper here. So you take that side channel information, you see how it affects the probability of getting one of the codes, and you calculate the min entropy there. And you put all of this into a graph where you look at the region where the intensity of the lead is found, and you see that it's pretty flat. Over the whole useful range, you're going to get a min entropy of at least 1.95 that you have at the output of it. So we're near optimal, actually, and then everything fits. So we know the device is working properly. There's other checks that need to be done, like correlation between pixels or subsequent frames. We have done that. I'm not showing them, but we haven't found any correlations like this, and that's normal, and that's from a mature technology such as CMOS image sensors. There's also an automatic failure detection mechanism, and actually it's interesting because this detection mechanism would fail before the entropy decreases. So if 5 years after the chips for a reason fails, it will not give you bad entropy before failing. It would just fail but it will have good entropy until it fails. So system level view looks like this. There's this DRBG there. So the DRBG is necessary to get certification in a secure application. So some people will want to have that, or some people will just take the quantum entropy and do that outside. If you want to do it, it is there, and you can get certification, security certification because of that. The architecture is compliant with NIST and AIS-31. It has integrated and live health checks with physical protection. Of course, if you shine light on the chip, it's not going to be seeing that light. It's all completely blocked. It works in a completely autonomous way with auto calibration and entropy source or the RNG data if you want. Operation modes can be. In terms of size, the smallest chip is 2.5 by 2.5 millimeter in size. It's pretty small. The biggest one is 4.2 by 5. The entropy rate of the biggest chip is up to 20 megabits per second, a very good rate, and it's necessary for pretty much all the applications out there at the moment. And the power of the smallest chip is as low as 50 milliwatts, and then you have a power down mode of 100 microwatts. So it is suitable for small handheld devices. So I'm not going to show the entropy test result and randomness test. We max out the outcome of the NIST 890B IID and non-IID test suite. Randomness test, we passed the test 822 and die harder with the expected rates. And both of these in varying environmental conditions. One of the chip has this automotive certification, which guarantees functionality in harsh environments, high temperature, low temperatures, and so on for the automotive sector. There's many applications for these, but I want to talk about one, which is the mobile phone. This year, IDQ, a Samsung collaboration with SKT, released a phone that has the QRNG chip in it. It's a Samsung A series phone. It's called the Samsung Galaxy Quantum. It's available for now only in South Korea. Hopefully, this chip is going to be available everywhere now. But it's, you know, we're very excited by this this outcome there. You know, it really seems that quantum technologies are making it out there, and I think, you know, in the next 10 years we're going to see a lot more of this. There's in the system, there's some applications that use that, payment services, cryptocurrency services, very popular in South Korea, and also some identification services, which benefit that from the randomness of the QRNG chip. Also, recently, IDQ just announced that there was another company that is going to be using the QRNG chip in its cell phone series. It's VinSmart in this Alias 5G smartphone. So hopefully more and more of devices will be using those. Okay, so there's a growing number of technologies, but I covered only these two here. What's important here is to have this, one of the things that's important is to have this clear and provable security in order to be able to use this in that. Okay, so that concludes the second part. I want to say thanks to the people who worked on this, Gaetan Graj and Wen Choi, Anthony Martin. And then there's a publication that's going to be appearing on the archive pretty soon on this topic. Okay, so that brings me to the conclusion. First part of the talk, I spoke about SnSPD tailored for fast QKD. We were able to speed up our SnSPDs and achieve 8 megabits per second of secret key rate at 50 kilometers in ultra low loss fiber, and we're working towards having much higher secret key rates. And then I spoke about IDQ's QRNG chip, talked about the detailed model of the entropy origin, and then the fact that we have near optimal entropy with the proven security and robust operations. And it's nice to see that these devices are now on cell phones. So with this, I conclude, and I thank you very much for your attention. Louis, I think you're muted.
Okay. Thank you very much, Felix, for this very nice talk.
Thank you.
Okay, so we're now ready to go and see the questions. Okay. Toshihiko Sasaki has a question. So now I have to find out if I can. Where is the participants?
Thank you for very much. Very nice talk. So,
okay. Oh, good.
Okay. Okay. So yeah, as for QRNG, intuitively, so your model is attenuated single photon, so it is it has some coherence. So intuitively, I agree with your model. But for example, random number cannot be checked from output. So we consider the origin of the entropy. So in this sense, I'm curious about how third party can check this device. So we can see the Poissonian distribution. Maybe that is not enough for. So how can? So I'm just kidding.
Yes. Okay. So you can. There is a okay. Right now we don't have a machine that you can just buy directly from us that allows you to check it. Although it's possible in principle, so it's possible to access the chip and then talk to it in such a way that you can control all the features. And you can, if you want, play with the intensity of the LED. You can switch off the LED and reproduce all the measurements that I showed here today. So all of this can be done on your end by having access to control of the chip and taking out the measurements. That's what we did. We just have this machine that allows us to control. We got the measurements. We didn't have to open the chip or anything. We just plugged it in and gathered the results and produced the data that I showed today.
But
does that answer your question properly?
If third party, yeah. So if third party does not believe your device, so maybe they random sample that and maybe check some devices, and in that sense, how they can check that. So maybe we will discuss later. So if other questions, so
yeah, with pleasure.
Yeah,
with pleasure. I'll be happy to do that.
No, thank you. Okay. Devda Sharma has a question. So maybe we can give him the let's see. Whoops. Where? How can I get participant? Spectator. Dev. I'm sorry. Okay, I'm going to unmute Dave the Sharma. Okay. Whoops. Okay, you can ask your question.
Hello.
Hi.
Okay, hi.
Hello.
Yes, we can hear you.
Hello.
Hello.
Hello. Can you hear me?
Yes.
Yeah, we hear you.
Yes, sir. I want to know that can we use this random number generator for banking system like password system, banking password type?
To generate a password, you mean?
Yes, for banking transfer of money like that.
Yes, absolutely. Any transaction that requires a transfer of confidential data can benefit from the QRNG, from the good randomness that you get out of it.
Yes. Thank you, sir.
My pleasure.
Okay, so I have another question from Jing Yan Hao. I'll try to. Okay, so I'm going to unmute Jing Yang Hao. Converser. Oh no. Well, I'm sorry. Okay, here. Good. Okay, you can ask your question, Ying Yan Hao.
Yeah. Thanks, Luis, and also thanks, Felix, for the nice talk. Indeed, I think it's good to bring the QRNG down to like really smaller level and then accessible. I think it's definitely a good approach. So I have two questions here that I'm curious. It's good that the whole random extraction is being simplified. The process of like taking the LSP, I think it's not very super rigorous, but I think it's practical. My question will be, when you say about passing needs tests, right? Are you referring to, so you also mentioned that there's an option where the user can used without the hash-based DRBG. So when you the test, is it prior to this unbiasing or afterwards?
So I'll try to, can I easily go back to the slide without, okay, I'll just go like this. Okay, so so your question is there any, well, okay, let me just go through it again and make sure that I explained it properly, so maybe that would answer your question. So the output there, as I explained, is this this set of random bits that go here, and this is just providing entropy bits. And in a security application, you need to have entropy source. And so this whole thing is the physical entropy source, quantum entropy source. And then this, in a security application, to get certification of the whole thing needs to go through a DRBG. That's just how the security standard is at the moment. Okay, so this part here is necessary. So it does unbiasing. Actually, if you start with a low entropy input, this will give the appearance of increasing the entropy at the output. However, if you start with the already a very high entropy input, this is only going to give you something that has less bits, but you cannot max out the entropy a lot more. So does that answer your question?
Yeah, so partly, yeah, I understand that. So after the, because it's the deterministic case, so in principle, yes, it shouldn't increase the entropy. So, but what I'm wondering is that at some point you show that with taking those two LSP, you can already see that the distribution is somewhat uniform. So yeah. I'm just wondering whether, yeah, you are already using, let's say, without this certification, can one already use it as random bits, for example? By random, I mean uniform, and also
yeah. So your question is if you take these bits here and feed them directly into the most rigorous tests, such as 822,
yes, that's right.
22, does it actually pass? And the answer is yes, it's going to pass. There's a little difference, but it's not, it's very small difference. So it does pass it actually.
Okay. Yeah.
But still, you know, in a sense, if you want to, the current state of things is that if you want to get a security certification, you have to use the RBG. So, you know, from a security point of view with certification, you have to use it, the RBG. But in principle, you could actually bypass it.
Okay, I see. Yeah, thanks. And that actually leads to my second question. So you also mentioned that you have done some mean entropy. That's also conditioned on the classical noises and so on. Yeah. So I'm just wondering if this, and then you also mentioned if something broken, and then it will probably still work on or guarantee until, I don't know. Yeah, I probably missed that part. But I'm just wondering, is the mean entropy estimation done, let's say, once at the factory, and then, or will it be checked, let's say, every now and then, or if there's a button where the user can press and say, okay, recalibrate my mean entropy, and then, yeah.
Yeah, so it's both actually. So it's done, of course, in the factory, but then at the in the chip itself, there is a lightweight entropy health checks that is being done live. So if this gets derailed, then you're going to get an error status popping up. So that's necessary to ensure the good. It's one of the health checks that is being done there. However, the retesting the entropy the same way that it's done in factory, you can't on the chip. However, you can, because it's too computationally demanding, but you can just output the bits yourself. If you want, you can embed the chip into a system and just sample and then do this live check yourself, you know, continuously run the entropy the entropy test the same way it's done in the factory, and in the way it's done in the standard of NIST 890B.
Okay.
Either IID or non-IID track.
I see. So you mean the, okay, yeah. Okay, maybe, yeah, I'll probably leave, I'll probably talk more afterwards, yes.
Okay.
Yeah.
At the meet and greet room, good.
Thanks.
Vadim Makarov has raised his hand, so I'm going to, okay, I think Vadim, you can talk. unless I'm.
Hi, Felix. Very nice development. The question about QRNG. So in this quantum entropy stream that is available off the chip, do you specify what is the randomness content of the stream? Do you specify that it might have a certain non-random fraction? Or so what is inside this ADC and filtering? Do you run some sort of hash function compression, or does the quantum entropy stream contain possibly a non-random component?
Well, if it gets out of the rail too much, then there's this help the status that is going to pick it up. And I'm sorry, I don't have the exact details of that. That's something we should discuss afterwards, just so we can dig into that. But I think one of the things I wanted to mention here today is that, by the way it works, and because of the way you actually continuously monitor different parameters of the image sensor and the output bits at the physical level and also at the entropy level. It's a lightweight check, as I mentioned, but you still do it. And also because of the way the chip works, I was showing this here, the intensity can drift on one side or the other, and you're still by design guaranteed to output very good entropy. And that's what I wanted to really emphasize here. And if it gets too close to the edge, then the chip is going to notify, recalibrate, and if the problem happens again, it's going to be stopped working, and it's going to tell you that there's a mistake going on, there's something wrong going on with the chip. So there you do have these checks, physical and mathematical checks of entropy happening in real time inside the chip.
Okay, I guess my question is, if you want a perfect random stream, do you need to run post-processing?
So perfect random. Well, okay. What the NIST 822 standard does, or statistical test suite does, and a dieharder as well, it runs an hypothesis check, an hypothesis testing procedure. So it looks at the output and it tells you if this is consistent with having an actual truly random source. Okay, so when you do that with the entropy right there, you have, of course, there's always some probability of failure that's intrinsic to the device, because a perfectly random source can once in a while, with a certain probability, output something that's not going to look random, and there's no way to tell. So you have to look at the rate at which you pass these different tests, and if you run it right there, you are going to pass with the appropriate rate. Now, if there's any unbiased, there's any remaining bias happening, you're going to be getting rid of it using this hash-based DRPG. So the important point is really that the device is made so that you have all the checks running simultaneously, so that you don't have to continuously run this. This 890B, sorry, the 822 randomness test is very computationally demanding. You cannot do that on the chip. You cannot do that on a small device running on battery. So the important point is to show that the architecture is simple enough so that it will not be in a situation where it's not failed and not producing good entropy. And that's what I tried to do during this presentation. Hopefully I was able to show you that this is actually the case.
Okay, I think we're pretty much done. But maybe may I ask a question, because there are no more questions and we're getting at the end. I mean, it's the dummiest of all questions. Is there something that prevents developing a random number generator that would achieve the maximum mean entropy, because you are at about 5% of the optimal for 2 bits? Is there something fundamental that could prevent that says that no implementation could have a maximum entropy without private simplification or randomness extraction? Would it be possible, or is it impossible? Is it proven impossible?
I have no idea. It's a very interesting question. Is there any no-go theorem to show that physically you cannot do that, that you cannot get randomness. I don't think so. I don't think quantum mechanics, for instance, says anything about that. But maybe there's something we haven't seen or don't know yet.
Yeah, because 5%, I find it amazingly close. I mean, I wouldn't have expected something like that.
Actually, maybe I can say something about this.
Yes, yes.
My guess is, of course, I know nothing about experiments, but pretty much in any experiment, whenever you use it, you're going to have a very small error rate. Let's say 5%. Maybe it's going to be a little bit lower, but it's always going to be constant. Given, like, if you use it n times, then that error rate is not going to go down with n, right? So you're going to have some epsilon times n error, and then at this point, you're going to have to do hashing anyway to get rid of this, right? Because you want the error rate to go down lower than that.
Unless you have a way to get rid of it somehow by I don't know.
But it's never gonna scale with n, right? Like, it's always gonna be some very small constant. You might make it very, very small, but then it's never gonna scale. It's never gonna go down with n. Right?
Yeah.
So I think hashing is inevitable because of this. But yeah.
Okay, so I think we're done. So thank you very much, Felix.
Thank you.
And the one who wants to talk further with him can go to the meet and greet room.
Yes, and indeed, actually, everybody is welcome now to join the meet and greet room, because that's also where we hold the poster session, which starts the first poster session, which starts right now. So